66 million years ago, an asteroid 10 kilometers wide traveled through space at 20 kilometers per second. Its trajectory, determined by millions of years of gravitational interactions with Jupiter, Saturn, and Mars, brought it toward Earth. The mathematics were precise. Impact was inevitable, except for one detail: 500 miles. That's the margin we're talking about. 500 miles of difference in trajectory. That's the distance from New York to Cleveland, from London to Edinburgh. A rounding error on a cosmic scale. And that 500 miles determined everything. In our timeline, the asteroid hit the Yucatan Peninsula. 10 billion Hiroshima bombs worth of energy released in an instant. Crater 180 kilometers wide. 75% of all species extinct. Every dinosaur larger than a chicken dead within months. But in an alternative timeline, one we're going to explore tonight, using actual science and real evidence, that asteroid's trajectory was 500 miles different. It entered Earth's atmosphere over the Pacific Ocean at too shallow an angle. It skipped, like a stone across water, but at cosmic scale. It tore through the atmosphere, created a fireball visible from half the planet, generated massive tsunamis that devastated Pacific coastlines, and then continued into space. Wounded, breaking apart, but gone. Earth survived, and so did the dinosaurs, which means something very simple and very disturbing. You wouldn't exist. None of us would, because in that timeline, mammals never got their chance. Before we explore what that world would look like, please consider subscribing. It genuinely helps us continue making content like this. Thank you. Tonight, we're asking what happens when you remove one cosmic accident and let evolution continue along the path it was already following. This isn't fantasy. This isn't science fiction. Every conclusion we reach will be based on real fossil evidence, documented evolutionary principles, and honest extrapolation from what we know about dinosaur biology and behavior. We have 165 million years of dinosaur fossil record to work with. We know how they lived, how they adapted, which species showed signs of increasing intelligence. And when we follow those trends forward, when we give them the 66 million years they lost to an asteroid, we get a timeline that's scientifically plausible and profoundly alien. By the end, you'll understand why that asteroid wasn't just bad luck for dinosaurs. It was extraordinarily good luck for us. The Chicxulub impact in our real timeline was catastrophic beyond comprehension. The asteroid struck shallow ocean over carbonate rock, vaporizing thousands of cubic kilometers of limestone. That released enormous quantities of sulfur and carbon dioxide into the atmosphere. The impact fireball reached space. Debris ejected beyond Earth's gravity fell back as molten rain. Wildfires ignited across entire continents. Then came the impact winter. Dust and aerosols blocked sunlight for months, possibly years. Global temperatures dropped 15 degrees Celsius. Photosynthesis stopped. Plants died. Herbivores starved. Carnivores followed. The food chain collapsed from bottom to top. 75% of species went extinct. Every non-avian dinosaur disappeared. The Cretaceous period ended in an afternoon, and in the ruins, small mammals emerged from burrows into a devastated but suddenly available world. That's our timeline. That's why we exist. But change the impact location by 500 miles, and everything changes. The asteroid enters atmosphere over deep Pacific Ocean. The angle is too shallow for direct impact. It skips. The physics are well understood. Objects entering atmosphere at low angles can bounce off if they don't penetrate deeply enough. This asteroid, weakened by its atmospheric passage, fractures and continues into space. Yes, there's destruction. The atmospheric entry generates a shockwave that shatters windows and collapses structures for 1,000 miles. The heat pulse ignites fires along coastlines. Tsunamis radiate outward, devastating Pacific islands and shorelines. Species dependent on coastal ecosystems suffer mass mortality, but inland regions barely notice. There's no global firestorm, no impact winter, no years of darkness. Plants continue photosynthesis. Herbivores continue grazing. Carnivores continue hunting. The global ecosystem remains intact. Within a year, coastal regions begin recovering. Within 10,000 years, the event is just a thin layer of unusual sediment in Pacific geological strata. Within 100,000 years, dinosaur populations return to pre-event levels. Life continues. But here's what doesn't happen. The ecological revolution that in our timeline gave mammals their opportunity never occurs. Dinosaurs remain dominant in every major ecosystem. Large theropods remain apex predators. Sauropods continue as megaherbivores. Ceratopsians, hadrosaurs, ankylosaurs fill every terrestrial niche. And mammals stay exactly where they'd been for 100 million years. Small, nocturnal, marginalized, prey animals. In our timeline, the extinction created opportunity, empty niches, available resources, reduced competition. Mammals exploded in diversity. Within 10 million years after the impact, they'd evolved into forms ranging from bat-sized to rhino-sized. Within 20 million years, whales had returned to oceans. Within 30 million years, primates had evolved. The asteroid's destruction was mammals' liberation. Remove that destruction, and mammals remain trapped. Any mammal lineage that tries to grow larger, that attempts to compete with dinosaurs for resources, gets outcompeted or eaten. Natural selection keeps them constrained to marginal niches. And critically, our ancestors, the lineage that would eventually produce primates and humans, never faces the evolutionary pressures that would select for larger brains, never develops complex social structures, never invents tools, never evolves language. The opportunity never comes. We never happen. But something else does. Late Cretaceous North America, forests of conifers, ferns and flowering plants, herds of triceratops migrating across floodplains and hunting them, moving through undergrowth with careful precision, a small theropod about the size of a large turkey, Troodon formosus. In our timeline, Troodon went extinct with all other non-avian dinosaurs. We know them only from fragmentary fossils. But those fossils tell a remarkable story. Troodon had the largest brain-to-body mass ratio of any known dinosaur. Not the largest absolute brain that belonged to massive sauropods, but the largest relative to body size. Their skulls show enlarged cranial cavities. Endocasts, fossil impressions of the brain case, reveal brain proportions similar to modern corvids. Ravens, crows, birds that solve multi-step puzzles, use tools, understand cause and effect, and plan for future events. Troodon, 66 million years ago, had similar neural architecture. They had stereoscopic vision, forward-facing eyes in the skull providing depth perception critical for hunting. Their eye sockets were enormous relative to skull size, suggesting exceptional visual acuity, possibly including night vision. Their hands possessed partially opposable digits capable of grasping prey and manipulating objects. Fossil nests show evidence of parental care and possibly communal nesting, suggesting social behavior. In every measurable characteristic, Troodon was already on an evolutionary trajectory toward increased intelligence. And in our timeline, they had perhaps 5 million years of that trajectory before extinction ended it. In this alternative timeline, they get 66 million years more. Intelligence is metabolically expensive. Human brains represent 2% of body weight, but consume 20% of caloric intake. For intelligence to evolve, the benefits must outweigh the costs. You need environmental pressures that make thinking advantageous. For Troodon, those pressures are clear. They're predators. Successful hunting requires planning, spatial reasoning, and pattern recognition. Stalking prey, predicting movement, coordinating attacks. They're social. Fossil evidence suggests group nesting. Social living requires communication, cooperation, and the ability to navigate complex relationships within groups. They have grasping hands. Manual dexterity enables object manipulation even at basic levels. And they face competition. Other predators threaten their resources. Other Troodon compete for mates and territory. Pressure selects for problem-solving ability. In our timeline, this evolutionary process had just begun. In this alternative timeline, it continues. 10 million years pass. Troodon populations diversify across North America and Asia. Some lineages grow larger, reaching the size of wolves. But more significantly, brain size increases disproportionately. Cranial capacity doubles in some species. Vocal structures become more complex, suggesting increasingly sophisticated communication. Hand dexterity improves. Claws reduce in prominence. Fingers become more flexible, and a critical transition begins. They start standing upright more frequently. Most theropods were already bipedal, but their posture was horizontal. Body balanced over hips, tail as counterweight, efficient for running. But for an intelligent species using tools, upright posture offers distinct advantages. It frees the hands completely for manipulation instead of balance. It elevates the head, improving sight lines and visual range. It changes biomechanics in ways that favor tool use over pure speed. In our timeline, human ancestors transitioned from quadrupedal to bipedal around 6 million years ago. For Troodon descendants, that shift happens around 50 million years ago in our calendar, 20 million years after the missed asteroid. The species that emerges doesn't have a name in our fossil record because it never existed here. But for our purposes, we'll call them dinosauroids. 20 million years after the asteroid miss, dinosauroids have spread across multiple continents. They stand approximately 5 feet tall, bodies lean and digitigrade, still showing clear theropod ancestry. The tail has shortened significantly, no longer needed for balance. The skull has enlarged and rounded to accommodate a brain now approaching human equivalent in size. Eyes remain large and forward-facing. The snout has shortened compared to ancestral forms. Hands possess 3 flexible fingers with reduced claws, capable of precision grip. And crucially, they use tools deliberately. Early tool use is simple. Rocks to crack open eggs or crush shellfish. Sticks to probe for insects or dig roots. But it's intentional. It's learned. It's transmitted from parent to offspring through observation and teaching. And once tool use establishes itself, it creates evolutionary feedback. Individuals better at manipulating tools acquire more food, survive more successfully, reproduce more often. Natural selection favors manual dexterity and the cognitive capacity to innovate. Brain size increases. Tool complexity increases. Each generation pushes slightly further. By 35 million years ago, dinosauroids manufacture stone tools, not just using found objects, but intentionally shaping them, striking one rock against another to create flakes with sharp edges. This represents a cognitive threshold. Stone tool manufacture requires planning. You must visualize the desired end product. You must understand fracture mechanics, at least intuitively. You must possess fine motor control to strike at precise angles with exact force. And you must be able to teach others. In our timeline, stone tools appear around 3 million years ago with early hominins. Dinosauroids reached this milestone 30 million years earlier. And then, around 30 million years ago, they discover fire. Fire is transformative. It provides warmth, extending habitat range into colder regions and seasons. It provides protection from predators and competitors. It enables cooking, which makes nutrients more bioavailable, reduces energy spent on digestion, and frees metabolic resources for brain development. And it creates social focal points where groups gather in evenings, strengthening bonds and enabling information exchange. In our timeline, controlled fire use begins around 1 million years ago. Evidence is debated, but it's recent. For dinosauroids, fire mastery happens 30 million years ago. They've had 29 million years longer than humans have existed to develop fire-based technologies and fire-centered cultures. The consequences are profound. Cooked food supports larger brains. Within 5 million years of fire mastery, dinosauroid cranial capacity exceeds human levels. Complex language develops, not just calls and signals, but grammar, syntax, abstract vocabulary. They tell stories. They pass knowledge across generations orally. They plan seasons in advance based on accumulated experience. Culture emerges. Different populations develop distinct dialects, customs, tool styles. And around 25 million years ago, they discover agriculture. Not accidentally, deliberately. They observe that seeds from preferred plants, scattered near settlements, grow into new plants the following season. They begin cultivating those plants intentionally, clearing land, planting, irrigating, protecting crops from herbivores, harvesting. In our timeline, agriculture begins around 12,000 years ago. It's the foundation of civilization, settled communities, food surplus enabling specialization, population growth. For dinosauroids, this revolution happens 25 million years ago. Villages appear along river valleys. Populations concentrate. Social complexity increases. Hierarchies develop. Leadership, trade, conflict, all the dynamics that drive civilizations forward. And they have 25 million years to develop before humans would even exist. By 20 million years ago, dinosauroids work metal, copper first, found in native form and beaten into tools and ornaments. Then smelting, using fire to extract copper from ores. Then bronze, an alloy of copper and tin requiring trade networks to acquire different materials from different regions. Metalworking represents sophisticated technology. It requires sustained high temperatures, understanding of material properties, and specialized knowledge passed through apprenticeship. In our timeline, the Bronze Age begins around 5,000 years ago. For dinosauroids, it begins 20 million years ago. They're building cities, not villages, but urban centers with populations in thousands. Stone architecture, planned streets, water management systems including aqueducts and sewers, defensive walls, public buildings, markets. In river valleys with reliable water and productive agriculture, civilization flourishes. Different regions develop distinct cultures. Coastal populations utilize marine resources, building ships for fishing and trade. Highland populations adapt to mountains, developing terrace farming and specialized architecture. Desert populations innovate water conservation. Cultural diversity emerges as it did in human history, but on vaster timescales. Kingdoms form. Empires rise and fall. Wars are fought with bronze weapons. History accumulates. And through it all, technology advances. Iron working develops. Steel follows. Mechanical engineering emerges. Water wheels harnessing rivers for power. Windmills. Complex pulley systems. Knowledge accumulates across generations. Writing systems develop to record transactions, laws, histories. Mathematics advances. Astronomy. They map stars, develop accurate calendars, create precise timekeeping devices. By 15 million years ago, dinosauroid civilizations span continents. They've invented the wheel, built roads connecting cities, established maritime trade routes. Everything humans associate with classical civilizations, they achieved millions of years earlier. But here's a critical question. Would their civilization look like ours? Would dinosauroids think like humans? Or would fundamental biological differences create an intelligence we'd barely recognize? The differences are significant. Dinosauroids evolved from reptiles. We evolved from mammals. Brain architecture differs. Modern reptilian brains rely more heavily on instinctive behaviors and learned responses encoded in different neural structures than mammalian cerebral cortex. Now, dinosauroids, with millions of years of brain evolution, might develop functionally similar cognitive capabilities through different pathways. Convergent evolution at the neural level. But the foundation remains different. Consider emotion. Mammalian emotion is tied to limbic system structures that evolved alongside parental care, social bonding, and temperature regulation. We feel empathy because our ancestors' survival depended on group cohesion. Reptiles generally exhibit less emotional range, more solitary, parental care minimal or absent, social bonds pragmatic rather than emotional. Troodon fossils suggest some parental care, but would that evolve into mammalian-style empathy over millions of years? Or would dinosauroid intelligence remain more calculating, understanding cooperation intellectually without feeling it emotionally? Their societies might function through logical self-interest rather than emotional connection. Laws exist because stability serves individual interests, not because harming others feels morally wrong. It's not evil, it's alien. Intelligence without the emotional framework we consider normal. That affects everything. Warfare potentially more brutal, unrestricted by moral considerations we take for granted. Scientific experimentation without ethical boundaries. Treatment of other species, including mammals, purely utilitarian. Another difference: temperature regulation. Dinosauroids descended from dinosaurs are likely mesothermic, not fully cold-blooded like modern reptiles, but not fully warm-blooded like mammals. Metabolism depends partially on external temperature. In cold weather or seasons, they become less active, sluggish. They might hibernate seasonally or migrate. Their cities would prioritize solar orientation. Architecture designed to maximize heat absorption and retention. cultural practices revolving around temperature cycles. Activity peaks in warmth, declines in cold. Their entire cultural rhythm tied to temperature in ways ours isn't. They'd also prioritize different senses. Reptiles rely heavily on vision, less on hearing and smell compared to mammals. Dinosauroids might develop primarily visual languages, complex color signaling, elaborate body language, auditory communications secondary. Their art would emphasize visual elements overwhelmingly. Music, if it develops at all, might be rudimentary compared to visual arts. Imagine a civilization where painting and sculpture dominate, but symphonies don't exist. Alien. And their hands. 3 fingers instead of 5. Tool design shaped by user anatomy. Different grips, different mechanical solutions. Their technology tree branches differently from ours at fundamental levels. Not inferior, not superior. Parallel. Different solutions to similar problems arising from different biological starting points. Now let's address something uncomfortable. While dinosauroids build civilizations, where are mammals? Where are our ancestors? The answer is exactly where they've been. Small, nocturnal, prey animals. In this timeline, primates never evolved beyond primitive tree-dwelling forms, similar to modern shrews. There's no evolutionary pressure for larger size or intelligence. Dinosauroids occupy every niche that in our timeline mammals would eventually fill. They're apex predators, dominant herbivores, intelligent tool users. Mammals remain marginalized, and some dinosauroid cultures domesticate them. Just as humans domesticated wolves into dogs, cattle, pigs, chickens, dinosauroids domesticate mammals. Small mammals bred for meat. Rodent-like creatures kept in pens, fed scraps, slaughtered young. Larger mammals, perhaps something resembling primitive primates, used as beasts of burden or food sources. Our direct ancestors, the lineage that would become humans, are livestock, farmed, eaten. This isn't cruelty from their perspective. It's pragmatism. Dinosauroids are intelligent, but they evolved from predators. Mammals have always been prey. That relationship continues. Some dinosauroid philosophers might debate whether mammals feel pain or possess awareness. The consensus would likely be no or irrelevant. Just as humans historically dismissed animal suffering, dinosauroids would view mammals as resources. And unlike our timeline where animal rights movements emerged from empathy, dinosauroid psychology might lack that emotional foundation entirely. Mammals remain food for 66 million years. By 10 million years ago, dinosauroid civilization reaches what we'd recognize as early industrial levels. Advanced metallurgy, steam power, mass production, printing presses spreading knowledge rapidly, universities, the scientific method formalized, knowledge accumulating across generations in written form. Mathematics, physics, chemistry, biology, all developing independently, but discovering the same natural laws we would. They map continents, navigate oceans with precision. Different civilizations establish global trade. And here's where they face a unique challenge: energy. Civilization requires energy. In our timeline, we burned wood, then coal, then oil, fossil fuels, ancient compressed organic matter from millions of years of accumulated plant and animal remains. But in this timeline, what are fossil fuels made from? In our timeline, Mesozoic oil deposits formed from marine reptiles and plankton that died in the Chicxulub extinction. In this timeline, those organisms didn't die en masse. They kept living. Those specific fossil fuel deposits don't exist. Carboniferous coal from 300 million-year-old forests remains, but Mesozoic oil is absent or drastically reduced. This forces dinosauroid civilization down different energy paths earlier. They can't rely on easy fossil fuel energy. They innovate. Water power extensively developed, wind power, and critically, geothermal energy. Volcanic regions provide heat, hot springs, geysers. For a species that needs external warmth anyway, geothermal energy is ideal. Cities built near volcanic regions, geothermal plants providing heat and power. This changes their industrial revolution. Cleaner, less polluting, but geographically constrained. Industrial centers must locate near geothermal sources. Control of volcanic regions means control of energy. Wars fought over them, and coastal civilizations developed tidal energy extensively, harnessing ocean tides for power. The technology develops earlier out of necessity. By 5 million years ago, dinosauroid civilization has achieved electrical power, telegraph communication, radio, mechanized transportation, aviation. Yes, flight. They've mastered powered flight. Aircraft designed for 3-fingered pilots, different control schemes, but functionally similar to ours. And they're reaching for space. Rocketry develops. Physics and mathematics advance to orbital mechanics. Astronomy reveals other planets they want to explore. And here's the staggering part. They succeed. By 4 million years ago, satellites orbit Earth. They've landed on their moon. Space stations under construction. Plans for interplanetary missions advancing. They're becoming a spacefaring species. While in our timeline 4 million years ago, our ancestors were Australopithecus, barely bipedal apes in Africa. The gap is incomprehensible. 62 million years of development. Technologies we can't imagine. Sciences we haven't discovered. Possibly post-biological existence. Digital consciousness. Interstellar exploration. Or perhaps they've hit limits we don't foresee. Perhaps physics constrains even advanced civilizations. We're working with one data point, ourselves, and we've barely started. But conservatively, dinosauroids by 4 million years ago have achieved everything we have and far more. And on Earth, mammals are still livestock. Small, stupid, farmed. Our ancestors never happened. But all of this, the cities, the technology, the spaceflight, it's extrapolation. Informed speculation based on evolutionary principles. So let's ground ourselves in something concrete, something real. In 1982, a paleontologist named Dale Russell did something remarkable. He created a dinosauroid. Dale Russell worked at the Canadian Museum of Nature in Ottawa. He specialized in late Cretaceous theropods, particularly Troodon. He studied the fossil evidence carefully. Brain-to-body ratios, hand structure, skeletal proportions. And he asked a scientific question. If Troodon had survived and continued evolving under selection for intelligence, what might it have become? So he constructed a model, not casually, not as fantasy, as rigorous scientific extrapolation. He worked with sculptor Ron Seguin, using comparative anatomy and evolutionary principles. They extrapolated forward, continued brain growth, continued selection for upright posture and tool use, and they created a life-sized sculpture. The result stands in the museum today. It's controversial. Critics argue Russell projected human evolution onto dinosaurs, creating something too humanoid. And looking at the sculpture, you see their point. It stands fully upright. Large rounded head, forward-facing eyes, shortened snout, 3-fingered hands. Body proportions eerily humanoid despite clearly reptilian features. scaled skin. But Russell defended his work with solid reasoning. He argued certain solutions are optimal for specific problems. If you're evolving intelligence and tool use, certain adaptations become nearly inevitable. Large brain requires large skull. Large heavy skull needs balance over center of gravity. That requires upright posture. Upright posture frees hands. Free hands enable tools. Tool use selects for dexterity and cognition. Each step follows logically. It's not that dinosauroids would look exactly human, but they'd face similar engineering constraints. Evolution, working with different materials, arrives at similar solutions. This is convergent evolution, and it's not speculative. It's documented throughout evolutionary history. Consider dolphins and ichthyosaurs. Dolphins are mammals. Ichthyosaurs were reptiles extinct for 90 million years. Completely different lineages separated by hundreds of millions of years of evolution. Yet they evolved nearly identical body plans. Streamlined fusiform bodies, dorsal fins, flippers, crescent tail flukes. Why? Because that shape is hydrodynamically optimal for fast swimming. Physics doesn't care about ancestry. Fluid dynamics apply equally to mammals and reptiles. Evolution discovers the same solution independently. Flight evolved independently at least 3 times. Birds from theropod dinosaurs, bats from terrestrial mammals, pterosaurs from early archosaurs. 3 separate origins, yet all developed wings, lightweight skeletons, similar aerodynamics. Because physics constrains options, there are limited ways to build a flying animal. Evolution finds them repeatedly. And intelligence. Intelligence evolved independently multiple times on Earth. Primates, obviously. Corvids, crows, and ravens, showing problem-solving comparable to great apes. Parrots demonstrating abstract reasoning. Elephants with complex social structures and long-term memory. Cetaceans, dolphins, and whales with sophisticated communication and cultural knowledge transmission. And octopuses. Octopuses are mollusks related to clams. Last common ancestor with vertebrates lived over 500 million years ago, before complex brains existed. Yet octopuses are remarkably intelligent. Tool use, problem solving, playful curiosity, individual recognition, all with a nervous system organized completely differently from vertebrates. Most neurons in their arms, not central brain. Distributed intelligence, yet functionally similar results. If intelligence can evolve in mollusks with alien neural architecture, if it evolves in birds lacking mammalian cerebral cortex, if it evolves repeatedly across vertebrates, then it can absolutely evolve in dinosaurs. Troodon already had the foundation. Large brain, binocular vision, grasping hands, social behavior. The trajectory was established. Russell's Dinosauroid wasn't fantasy. It was following that trajectory logically forward. Russell's specific model has limitations. Modern paleontologists note he made assumptions about posture and proportions that may not hold perfectly. Troodon hip structure might not support fully vertical stance without significant redesign. The tail couldn't simply vanish without major balance implications. Hand proportions might develop differently. These are valid technical critiques. Russell's Dinosauroid probably isn't exactly what evolved Troodon would look like. But the principle remains sound. Given millions of years and selection for intelligence and tool use, Troodon or descendants would evolve in that general direction. Intelligent, bipedal, manipulative, capable of complex behavior and technology. That's scientifically defensible. And the sculpture serves its purpose. It makes the abstract concrete. It forces us to confront the possibility that intelligence isn't uniquely mammalian, that consciousness could have evolved in scales instead of fur, that our existence isn't inevitable but contingent on specific events. One event in particular. 66 million years ago, the asteroid did not miss. That's our actual timeline. It hit the Yucatan with unimaginable force. 10 billion Hiroshima bombs, crater 180 kilometers wide. The impact vaporized rock, ejected debris into space, created global firestorm. Sulfur aerosols blocked sunlight for years. Global temperatures plummeted. Photosynthesis stopped. 75% of species went extinct. Every non-avian dinosaur died. Not because they were failures. Dinosaurs were spectacularly successful. 165 million years of dominance across every terrestrial ecosystem and many marine ones. They survived continental drift, climate shifts, volcanic events, ice ages, competitors. They adapted, diversified, thrived. And they died in an afternoon because a rock from space hit the wrong place at the wrong time. They couldn't prevent it, couldn't see it coming, had no defense, just catastrophically bad luck. And that bad luck was extraordinarily good luck for us. The extinction created opportunity, empty niches, available resources, and small mammals emerged from hiding into a devastated but suddenly accessible world. They diversified rapidly. Within 10 million years, mammals filled roles dinosaurs once held. Within 30 million years, primates evolved. Within 60 million years, hominins appeared. And 300,000 years ago, US. Homo sapiens, asking questions, imagining alternatives, understanding our own contingency. We didn't outcompete dinosaurs. We inherited their catastrophe. And the rocks are still out there. Right now, NASA tracks 28,000 near-Earth objects, asteroids whose orbits cross Earth's path. Most are small, posing no significant threat, but some are large. And a few, very few, are Chicxulub scale, civilization ending, species ending. And they're coming. Not today, probably not in our lifetimes, but eventually. An asteroid between 100 meters and 1 kilometer across hits Earth roughly every 1,000 years. Tunguska, Siberia, 1908. 50 meters wide, 15 megaton explosion, flattened 2,000 square kilometers of forest. Pure luck it hit empty wilderness. 6 hours later, Earth's rotation would have placed Moscow in the impact zone. Millions dead. History altered. On April 13, 2029, an asteroid named Apophis will pass 31,000 kilometers from Earth. That's closer than geostationary satellites, visible to the naked eye, and Earth's gravity will deflect its orbit. We can't predict exactly how much, which means we can't be certain where it will be when it returns in 2036. Probably safe, probably misses by wide margins, but not certainly. That's the reality. Rocks in space following orbital paths determined by gravity, occasionally intersecting with planets. When they do, size determines consequences. We're the first species in Earth's history capable of seeing them coming. Dinosaurs couldn't detect asteroids, couldn't calculate trajectories, couldn't build defenses. They had no warning and no options. We do. We have detection systems. We're developing deflection capability. NASA's DART mission in 2022 successfully altered an asteroid's orbit by impacting it with a spacecraft. Proof of concept. We can move space rocks, not large ones yet, not Chicxulub scale, but we're learning. If we have warning, decades ideally, we might survive what dinosaurs couldn't. We might be the first intelligent species to break the extinction pattern. Or we might not. We might detect threats too late, might lack political will to fund deflection systems, might fail technically. And if we do, we join the fossil record. Another intelligent species that almost made it. That built civilizations and reached for stars and got obliterated by cosmic chance they couldn't prevent. Future paleontologists, whatever species they are, will study our layer and wonder what we might have become. Just as we studied Troodon fossils and imagined dinosauroids. That asteroid gave us the world. 500 miles of difference between one timeline and another. Between dinosaur civilization and mammalian civilization. Between reptilian intelligence and human intelligence. Between their existence and ours. We got lucky. Incomprehensibly, statistically, absurdly lucky. And the next asteroid will test whether luck is enough. Whether intelligence confers survival advantage against cosmic threats. Whether consciousness can persist beyond single planets. Dinosaurs failed that test. They couldn't pass it. They lacked the tools. We have tools. Detection, tracking, deflection capability under development. The question isn't whether we're special. We're not. We're one evolutionary experiment among countless others. The question is whether we use what we have. Whether we prioritize survival over short-term interests. Whether we build infrastructure to see threats coming and move them aside. That determines whether intelligence has a future, whether consciousness persists, or whether it's just a brief flicker that occasionally appears when matter organizes itself into thinking patterns, looks at stars, asks questions, and then goes dark again. 66 million years ago, cosmic chance sealed one timeline and opened another. We didn't earn this. We inherited it. The only question that matters is what we do with the time we're given. And somewhere out there, another rock is following its orbit, heading toward us. The clock is ticking, and we're about to learn whether we deserve the world that asteroid gave us. That asteroid gave us the world. 500 miles of difference between one timeline and another. Between dinosaur civilization and mammalian civilization. Between reptilian intelligence and human intelligence. Between their existence and ours. We got lucky. Incomprehensibly, statistically, absurdly lucky. And the next asteroid will test whether luck is enough. Whether intelligence confers survival advantage against cosmic threats. Whether consciousness can persist beyond single planets. Dinosaurs failed that test. They couldn't pass it. They lacked the tools. We have tools. Detection, tracking, deflection capability under development. The question isn't whether we're special. We're not. We're one evolutionary experiment among countless others. The question is whether we use what we have. Whether we prioritize survival over short-term interests. Whether we build infrastructure to see threats coming and move them aside. That determines whether intelligence has a future, whether consciousness persists, or whether it's just a brief flicker that occasionally appears when matter organizes itself into thinking patterns, looks at stars, asks questions, and then goes dark again. But let's step back for a moment and consider what this alternative timeline really means. Not just for us, but for the concept of intelligence itself. Because if dinosaurs had continued evolving, if Troodon descendants had developed civilization millions of years before primates even existed, it would fundamentally challenge our assumptions about what intelligence is and where it comes from. We tend to think of intelligence as something uniquely mammalian, something tied to warm blood, parental care, complex social structures, emotional bonding. We assume consciousness requires empathy, that civilization requires compassion, that technology emerges from cooperation rooted in emotional connection. But what if that's wrong? What if intelligence is substrate independent? What if consciousness can emerge from any sufficiently complex neural network, regardless of the emotional architecture surrounding it? Dinosauroids would prove that thesis. They'd be intelligent without mammalian emotional frameworks. They'd build civilizations without empathy as we understand it. They'd cooperate through rational self-interest rather than emotional bonding. And they'd be just as successful, possibly more so, than we are. Think about what that means for our search for extraterrestrial intelligence. We're looking for signals from space, radio transmissions, laser pulses, signs of technological civilizations. But we're unconsciously assuming those civilizations will be something like us. Perhaps not humanoid, but psychologically similar, motivated by curiosity, driven by emotional needs, organized around social bonds. We imagine first contact as communication between minds that share fundamental values. But what if alien intelligence is more like dinosauroids than humans? What if it's cold, calculating, pragmatic? What if alien civilizations lack empathy entirely, viewing other species purely as resources or threats? What if their technology is advanced, but their ethics are incomprehensible to us because they evolved from predators without mammalian social bonding? First contact might not be a meeting of minds. It might be encountering intelligence so alien we can't establish common ground. They'd be conscious, aware, capable of science and philosophy and art. But their values, their motivations, their very experience of consciousness might be fundamentally different from ours. And we'd have no framework for understanding them. That's what dinosauroids represent, not just an alternative history for Earth, but a glimpse of what alien intelligence might actually be like. Different, functional, successful, but alien in ways we haven't prepared for. Now, consider the implications for artificial intelligence. We're creating machine intelligence right now. Neural networks learning from data, systems that can play chess, recognize faces, generate text, drive cars. And as these systems become more capable, we're asking whether they're conscious, whether they have subjective experience, whether they deserve rights. But we're judging machine consciousness by mammalian standards. Does it show empathy? Does it form social bonds? Does it experience emotion? Those might be irrelevant questions. Machine intelligence, if it becomes genuinely conscious, might be more like dinosauroid intelligence than human intelligence, capable of complex reasoning without emotion, able to cooperate without bonding, intelligent without empathy. And we'd be making a category error if we judged it by human psychological standards. Dinosauroids would teach us that intelligence comes in fundamentally different forms. That consciousness isn't one thing, but many possible things. That our experience of awareness, rich as it feels, is one implementation among countless potential implementations. This matters because as we develop artificial intelligence and as we search for alien intelligence, we need to recognize that minds unlike ours are possible. That intelligence doesn't require human psychology. That consciousness can exist in forms we might not even recognize as conscious because they lack the emotional markers we associate with awareness. let's return to evolutionary timescales. Because the truly staggering thing about this alternative timeline isn't just that dinosauroids would exist, it's how much time they'd have. 66 million years of continued development after the point where in our timeline, dinosaurs went extinct. To put that in perspective, 66 million years ago in our actual timeline, the asteroid had just hit. Mammals were small. Primates didn't exist. Hominins were 63 million years in the future. Modern humans were 65,700,000 years in the future. Everything we call human history, from stone tools to agriculture to writing to industrialization to space travel, happened in the last few 100,000 years. A blink, a fraction of a percent of 66 million years. Now imagine giving a species 66 million years of continuous development. No reset button. No extinction event forcing them to start over. Just continuous accumulation of knowledge and technology across millions of years. What would they achieve? We can barely imagine. In our timeline, technological progress is accelerating. From first flight in 1903 to moon landing in 1969. 66 years. From first computers in the 1940s to smartphones in the 2000s. 60 years. The pace increases exponentially. Now extend that not for decades or centuries, but for millions of years. After 1 million years of continuous development, assuming they avoid self-destruction, dinosauroids would have technology we can't begin to describe. Mastery over matter at atomic scales, energy generation from vacuum fluctuations or direct matter conversion, computation using quantum effects or exotic physics we haven't discovered. After 10 million years, they might be post-biological, digital consciousness, minds running on substrate far more efficient than biological neurons, immortal unless destroyed by external forces, capable of thought at speeds biological brains can't approach. After 66 million years, they might not even be recognizable as physical beings. They might exist as information patterns distributed across networks spanning solar systems. They might have spread to other stars, colonized other planets, encountered other species. Or they might have transcended physical reality entirely in ways we can't conceptualize because our physics is incomplete. This sounds like science fiction, but it's extrapolation from known principles. Intelligence enables technology. Technology enables control over environment. Control enables survival and expansion. Time scales matter enormously. Give any intelligent species enough time without extinction, and they'll develop capabilities that look like magic to earlier stages. Humans went from bronze tools to nuclear weapons in 5,000 years. From animal power to rocket engines in 200 years. The curve is exponential. Extend it for millions of years, and you get something beyond our comprehension. Dinosauroids would have had that time. They'd be to us as we are to bacteria, not just more advanced, operating on entirely different levels of reality. But here's a darker thought. What if they didn't make it? What if intelligence, regardless of form, hits limits? What if every civilization, given enough time, eventually destroys itself or stagnates? We see this possibility in our own development. Nuclear weapons capable of extinction, climate change threatening ecosystems, artificial intelligence potentially surpassing human control, synthetic biology enabling engineered pandemics. The same intelligence that lets us split atoms and manipulate genes also gives us tools to destroy ourselves. And the timescales are short. We went from first controlled nuclear reaction in 1942 to Cuban Missile Crisis in 1962. 20 years, from invention to near apocalypse. We've had nuclear weapons for 80 years and haven't destroyed ourselves yet, but that's a tiny fraction of evolutionary time. The question isn't whether we can avoid self-destruction for decades. It's whether we can avoid it for millennia, for millions of years. And we don't know if that's possible. Maybe every intelligent species faces a filter, a point where their technology becomes dangerous enough to destroy them. Most don't pass through. They invent something they can't control, or they deplete their planet's resources, or they war with each other using weapons too powerful to survive. The universe might be filled with ruins of civilizations that almost made it. That developed intelligence, built technology, reached for the stars, and then vanished. Dinosauroids would face the same filter. Maybe they'd pass through. Their different psychology, lacking mammalian aggression and emotional volatility, might help. Or it might not. Intelligence without empathy might be more dangerous, more willing to risk extinction for marginal advantages. We don't know. What we do know is that in our actual timeline, intelligence has existed on Earth for a geological instant. Modern humans, 300,000 years. Civilization, 10,000 years. Industrial technology, 200 years. Space technology, 60 years. That's nothing. That's a pixel on the timeline of Earth's history. Dinosaurs existed for 165 million years. 165 million years of continuous presence on every continent, in every major ecosystem, adapting to every climate. We've had 300,000. We're infants. We haven't proven anything yet. We haven't demonstrated that intelligence is a long-term survival strategy. We haven't shown that consciousness persists beyond brief moments in geological time. We're an experiment in progress, and the jury is still out. Dinosaurs succeeded for 165 million years before an asteroid ended them. We've succeeded for 300,000 years, and we're already facing existential threats of our own making. Climate change, nuclear weapons, biological warfare, artificial intelligence, nanotechnology. We're creating tools we might not be able to control. And unlike dinosaurs, we can't blame an asteroid. If we go extinct in the next 1,000 years, it'll be our fault. We'll have had the intelligence to see threats coming and the capability to prevent them, but we'll have lacked the wisdom or the will. That would be a new kind of extinction. Not cosmic bad luck, not natural catastrophe, self-inflicted, intelligence destroying itself. This brings us back to the fundamental question. If the asteroid had missed, if dinosaurs had continued, if Troodon descendants had developed intelligence and civilization millions of years ago, would they still exist? Or would they have destroyed themselves long before reaching our present? We can't know. But the question matters because the answer tells us something about the future of intelligence in the universe. If intelligence inevitably leads to self-destruction, then the universe might be full of dead civilizations. Brief flickerings of consciousness that ignite, burn bright for a few thousand years, and extinguish. If that's the pattern, then we're doomed regardless of asteroids. Our intelligence itself is the threat. But if intelligence can survive its own adolescence, if civilizations can mature past the point where they're capable of self-destruction, then consciousness might persist, might spread, might fill the universe. Dinosauroids, given 66 million years, would have answered that question. If we could look at the alternative timeline and see them thriving, expanding, exploring, that would tell us survival is possible. That intelligence can be stable long-term. But if we looked and saw ruins or silence or a dead planet stripped of resources, that would tell us something else. That intelligence is self-limiting. That consciousness is a brief evolutionary experiment that usually fails. We don't get to look at that timeline. We only have our own. And in our timeline, the test is happening right now. Let's talk about one more aspect of the dinosauroid scenario. If they had developed civilization, what would their culture look like? We've discussed their biology, their technology, their potential differences in psychology. But what about art, music, literature, philosophy? Would they create beauty? Would they ask why questions or only how questions? This matters because it gets at what consciousness really is. Is it just information processing, problem solving, tool use? Or is there something more? Something about subjective experience that leads inevitably to aesthetic appreciation and existential questioning. Humans create art. Every human culture, without exception, produces music, visual art, storytelling, dance. Even in the harshest conditions, even when survival is difficult, humans make beauty. Why? It's not obviously adaptive. Painting doesn't help you hunt. Music doesn't improve survival directly. Yet we do it compulsively. It seems consciousness, human consciousness at least, includes an aesthetic dimension. An appreciation for pattern, harmony, novelty. A drive to create and experience beauty. Would dinosauroids share that? Or is aesthetic sense tied to mammalian neurology? Maybe reptilian consciousness would be purely functional, focused on practical problems, survival, resources, competition. Beauty might be meaningless to them. Their cities would be efficient but not decorative. Their communication would convey information but not poetry. Their science would answer how but never why. Or maybe aesthetics emerges from any sufficiently complex consciousness, regardless of substrate. Maybe the ability to recognize patterns, which intelligence requires, inevitably leads to appreciating elegant patterns. Mathematical beauty, symmetry, complexity balanced with order. Maybe dinosauroids would have art, but alien art. Visual arts, probably, given their vision-dominant senses. Elaborate color patterns, sculptures playing with form and shadow. Architecture that's beautiful by their standards, even if alien to ours. Music might not develop, or might be very different. Rhythmic visual patterns instead of auditory ones. Synchronized movement creating dynamic art. And philosophy. Would they ask the big questions? Why does anything exist? What is consciousness? Is there meaning to existence beyond survival? Or would those questions seem pointless to minds without human anxiety and existential dread? Maybe cold rationality concludes there is no why, only how, and that's sufficient. No need for meaning. No need for purpose beyond continuation. Just existence, consciousness experiencing itself, building and creating and exploring, because that's what intelligence does. Not for some grand purpose, just because it can. That might be more honest than our desperate search for meaning. Or it might be missing something essential about what consciousness is. We don't know. We only have human consciousness to examine from the inside. Everything else is inference and speculation. But here's what we can say with confidence. If dinosaurs had survived, if intelligence had evolved in reptiles instead of mammals, the result would be genuinely alien. Not just different in degree, different in kind. A form of consciousness that shares some functional capabilities with ours. Problem solving, planning, communication, technology, but built on different foundations. Different emotional architecture, different sensory priorities, different evolutionary history shaping different values. And encountering such intelligence, whether hypothetical dinosauroids or actual aliens from another world, would be profoundly challenging. We wouldn't be able to assume they think like us, that they share our values, that they want what we want. Communication might be possible, since any intelligence capable of technology must understand mathematics and logic. But deeper understanding might be impossible. We might trade information about physics and chemistry, might establish basic cooperation through mutual self-interest. But we might never truly understand their subjective experience, never grasp what it's like to be them. Just as we can't really know what it's like to be a bat, or an octopus, or an AI, we couldn't know what it's like to be a dinosauroid. They'd be conscious, aware, but their consciousness would be alien, and that's simultaneously fascinating and unsettling. Now let's bring this back to Earth, to our actual history, to the moment 66 million years ago when everything changed. The asteroid hit. That's the fact. The simple, brutal, world-changing fact. 10 kilometers of rock traveling at 20 kilometers per second struck the Yucatan Peninsula. In an instant, everything transformed. The impact released energy equivalent to 10 billion nuclear weapons. The explosion was visible from space. The fireball reached the upper atmosphere. An earthquake larger than any in recorded human history propagated through the planet. Tsunamis hundreds of meters tall radiated outward, devastating coastlines thousands of kilometers away. The impact winter followed. Dust and sulfur aerosols blocked sunlight for months or years. Temperatures plummeted. Plants died. Herbivores starved. Carnivores followed. 75% of species on Earth went extinct. The Cretaceous period ended. The age of dinosaurs closed. And in the ruins, small mammals inherited a devastated but available world. That's our origin story. Not gradual, not inevitable, catastrophic, sudden, complete restructuring of global ecosystems in an afternoon. Everything we are traces back to that moment. Every human ancestor survived because they were small enough, adaptable enough, lucky enough to make it through the years of darkness and cold. And when the dust settled and the sun returned, they found a world without the competitors and predators that had constrained them for 100 million years. They evolved, diversified, grew, and eventually we happened. But it didn't have to be that way. 500 miles. That's the margin we've been exploring all evening. 500 miles of difference in asteroid trajectory. Hit deep Pacific instead of shallow Caribbean. Skip instead of impact. Localized catastrophe instead of global extinction. And evolution continues down a different path. Dinosaurs adapt to regional disruption and recover. Mammals remain constrained. And 66 million years later, the world belongs to intelligent reptiles who've had time to develop technologies we can barely imagine. That timeline is real in the sense that it was possible. The physics allowed it. The asteroid's trajectory had uncertainty, Gravitational interactions with other bodies created a probability distribution of impact locations. Yucatan wasn't certain. It was one point on a curve. The dice rolled, and they came up Yucatan. But they could have rolled differently, and if they had, none of us would be here to know it. Not because we'd have been killed, because we'd never have existed. The entire mammalian radiation that led to primates, to hominins, to humans, it all depended on that extinction event. Remove it, and the path never opens. We're not inevitable. We're not the crown of creation. We're not evolution's goal. We're one possible outcome that happened because specific conditions occurred in specific sequence. Change any major variable, and you get a different outcome. Perhaps no intelligent species at all. Perhaps intelligence in insects. Perhaps intelligence in cephalopods. Or perhaps dinosauroids. Conscious, civilized, spacefaring reptiles building their own history while mammals remain in the trees. Unchanged, irrelevant, prey animals for 66 million years. That's the timeline we avoided. Not through merit, through chance, through an asteroid hitting in one specific location instead of another. And here's what that means for how we think about ourselves and our future. We're not special. We're lucky. We happen to be the lineage that got the opportunity. That doesn't make us better than dinosaurs. They succeeded for 165 million years. We've succeeded for 300,000. They're not failures. They're victims of cosmic bad luck. And we're not superior. We're beneficiaries of their catastrophe. That should make us humble. Should make us recognize that intelligence, consciousness, civilization, all of it is fragile, contingent, temporary unless we actively work to make it permanent. And that brings us to the present, to right now, to the moment we're living in, because the rocks are still out there. The asteroid that killed the dinosaurs wasn't unique. It wasn't the first large impact Earth experienced, and it won't be the last. Impacts are ongoing, regular, predictable statistically, if not individually. Small asteroids hit Earth daily, burning up in atmosphere as meteors. Larger objects hit every century or so, causing regional damage. Tunguska-scale events every 1,000 years. Chicxulub-scale events every 100 million years on average. We're due. Not tomorrow, not next year, but eventually. And when the next big one comes, we'll face the same test dinosaurs faced. Can we survive it? The difference is we have tools they didn't. We have detection systems, telescopes scanning the sky continuously, tracking objects, calculating orbits. We catalogue near-Earth asteroids. We know where most large objects are. Not all, but most. And we're developing deflection capability. NASA's DART mission in 2022 was a proof of concept. A spacecraft deliberately crashed into an asteroid to change its orbit. It worked. The impact altered the asteroid's trajectory measurably. We proved we can move space rocks. Not large ones yet. Not Chicxulub scale. But we're learning. We're building capability. If we detect a threatening asteroid decades in advance, we might be able to deflect it. Might be able to nudge its orbit just enough to miss Earth. 500 miles of difference. That's all it takes. We can create that difference if we have warning and resources and will. That's new. That's unprecedented in Earth's history. For 4 billion years, life on this planet was helpless against cosmic impacts. Species lived or died based purely on luck. Where they were when the rock hit, whether they were adaptable enough to survive the aftermath. But now, for the first time, one species has the potential to see impacts coming and do something about it. That's remarkable. That's genuinely new. Intelligence might confer survival advantage against extinction events, might break the pattern where catastrophes randomly reset evolution, but we haven't proven it yet. We have the beginning of capability, but not full implementation. We're tracking some objects, but not all. We've deflected one small asteroid in a test, but couldn't handle a large one yet. And we haven't demonstrated the political will to fund these systems adequately, to make planetary defense a priority, to invest resources in preventing something that probably won't happen in our lifetimes, but certainly will eventually. That's the test. Can we think long-term? Can we act on threats that are statistically certain but temporally distant? Can we overcome the tendency to focus on immediate concerns and ignore slow-moving disasters? Because this applies to more than asteroids. Climate change. Same problem. Certain. Deadly. But gradual enough that we can ignore it in the short term. Artificial intelligence risks. Same thing. Potentially existential, but not obviously urgent until possibly too late. Synthetic biology, nanotechnology. Every powerful technology creates risks that are long-term and abstract, easy to ignore, easy to deprioritize. But collectively, they determine whether intelligence is a viable long-term strategy, whether consciousness persists or flickers out. And we're right at the critical point. The point where our technology is powerful enough to threaten us, but we haven't yet developed the wisdom to manage it safely. Dinosaurs didn't face these challenges. They didn't have technology, didn't have the capability to threaten themselves. Their extinction was external. Ours might be internal. We might be the first species intelligent enough to cause our own extinction. That's novel. That's a test dinosaurs never took, and we don't know if we'll pass. We're living through the experiment right now. Every decision we make about climate, about weapons, about artificial intelligence, about pandemic preparedness, about asteroid detection, every decision is part of the test. Are we wise enough to survive our own intelligence? Can consciousness persist despite having tools that can destroy it? The answer determines not just human future, but the viability of intelligence as an evolutionary strategy. If we fail, if we go extinct in the next few centuries, we'll have answered the question negatively. Intelligence leads to self-destruction. The universe is probably full of dead civilizations that prove the same thing. But if we succeed, if we navigate through this critical period and establish sustainable civilization that persists for millions of years, then we'll have proven something important. That consciousness can be stable, that intelligence can manage its own dangers, that awareness can persist indefinitely once it emerges. That would be genuinely significant, not just for us, but for the principle, for what it means about consciousness in the universe. So, where does this leave us, with a story about an asteroid that missed versus an asteroid that hit? With a hypothetical timeline where intelligent reptiles build civilizations while mammals stay small. With real fossil evidence showing that dinosaurs, particularly Troodon, were on an evolutionary trajectory toward intelligence. With Dale Russell's sculpture concretizing what evolved intelligence might have looked like. And with the knowledge that our existence, everything we are, depends on specific events happening in specific ways. We're not inevitable. We're contingent. We're the outcome of one particular sequence among countless possible sequences. But we're here, conscious, capable of understanding our own history and imagining alternatives, capable of asking what if and following the implications, and capable, for the first time in Earth's history, of protecting ourselves against the kind of catastrophe that killed our predecessors. That's where we stand, at a unique moment, where intelligence has developed technology that might, possibly, allow survival beyond what natural selection alone provides, where we can see threats coming and theoretically prevent them, but where we haven't yet proven we will. The story of the dinosaurs isn't just about the past, it's about the future. Their extinction gave us opportunity. What we do with that opportunity determines whether intelligence has a future at all, whether consciousness persists, or whether it's just a brief anomaly, a temporary complexity that emerges, exists briefly, and vanishes, leaving the universe dark again, unconscious, unaware, the way it was for 13 billion years before the first minds emerged to ask why. 66 million years ago, an asteroid sealed one timeline and opened another. 500 miles made all the difference. We inherited the ruins of that impact. We're building on a foundation of mass extinction. Everything we've accomplished, every piece of art, every scientific discovery, every moment of human experience exists because that rock hit in exactly the right place to kill exactly the right species at exactly the right time. We didn't earn this. We're just here, making the most of it. And the question we face, the test we're taking right now, is whether we can keep it. Whether we're wise enough to see the next rock coming and move it aside. Whether we're careful enough to manage the technologies we're creating. Whether we're thoughtful enough to plan beyond our own lifetimes. Whether intelligence, this improbable emergence of consciousness from unconscious matter, can persist. Or whether it's self-limiting. Whether we're just another layer in the fossil record waiting to be discovered by whatever comes next. That's the question. And we're living the answer right now. Every day. Every choice. Every decision about priorities and resources and values. The experiment continues. And the outcome will determine whether that asteroid 66 million years ago was the beginning of something permanent or just a temporary disruption before silence returns.